introduction. And great to see everyone. Sorry we can't be together in person, but this is the next best thing. Anyway, as Brian mentioned, I'll be presenting some work on extratropical persistent anomalies. And my collaborators, a lot of the work I'll be showing is due to Rebecca Miller, who is a master's student, Allison Michaelis, who's a PhD student, and Greg Tierney, who is a postdoc. They've all moved on to other positions as listed, but a lot of their work will be in this talk. And my collaborator at NC State is Walt Robinson. He and I were co-PIs on the grant, the NSF grant that funded this work, which is now in its third no-cost extension, I think, or something like that. It's pretty much winding down. So let's start with a little story. You may have heard of Litton, British Columbia. It's about 90 miles northeast of Vancouver. Here it is on Google Maps. And if we go to last June 27th, Litton broke the all-time Canadian maximum temperature record at 116 degrees Fahrenheit. However, they weren't done, because the next day they broke the all-time record at 118. And then on Tuesday, the 29th, they broke it again with 121 Fahrenheit. This is up in interior British Columbia. But then things went downhill from there. The town was evacuated the next day, and then it burned. 90% of the town burned in a fire right after that. The pictures are stunning from that event. And as far as I know, rebuilding efforts have been very slow in Litton. So what was happening? What caused this? Well, you can look at this larger picture of the Western North American heat wave. I grew up in Seattle, Washington, and this NASA image shows that surface temperatures between 40 and 50 Celsius throughout the Seattle metropolitan area, urban heat island effect. The 2-meter air temperature anomaly, see this very large area of practically maxed out temperature anomalies. There's a wiki page about this heat wave. It was a remarkable event, over 1,400 fatalities, almost evenly split between British Columbia and the Pacific Northwest. So it's a high impact event. The estimated cost was $8.9 billion US dollars. Fire, heat, crop losses, a lot of things happened here. Portland, Oregon, if you look at this, this is one of these annual, the average high and low, and then the record envelope shown. This heat event from last June stands so far above anything that ever happened there before. It was just jaw-dropping. They broke their all-time record on 3 straight days, and Portland as well, culminating with 116 degree Fahrenheit. The World Weather Attribution Group immediately went to work on this case, and by July 7th, they had come to the conclusion that this event would have been virtually impossible without anthropogenic climate change. And they're on the webpage, they have all their methods. You can download the full PDF documentation. Now, meteorologically, this diagram here, this shows a Hofmolar diagram with time increasing downward. So it starts in mid-June and ends on July 10th, 2021. And what's shown in the alternating cool and warm colors is the upper level geopotential height anomaly. So you can see where you have the cool colors, that's a trough, and where you have the warm colors, that's a ridge. And so this is the ridge in question. Here's 120 west longitude. So this warm strip here is the persistent anomaly that was associated with this heat wave. And you can see it was part of this wave train, which is pretty strong. That's a pretty strong Rossby wave train for late June out across the Pacific. So, but we're interested in this ridge. I mean, you can see this ridge was a persistent feature. And if you look at the 500 millibar, geopotential height and the eddy height, the deviation from the zonal mean, you can see this really impressive looking upper level ridge over centered over southern British Columbia. So this talk is about persistent anomalies, and this is the persistent anomaly that was responsible for the Western North America heat wave last June. And so we have lots of questions about these, but I thought I would just start by saying, well, what is a persistent anomaly? A slow moving high or low pressure system meeting some intensity or duration threshold. The anomaly can be defined in different ways, typically relative to a time or a climatological average. Now, blocking and persistent anomalies are not synonymous. Blocks are a subset of persistent anomalies. We'll talk more about that in a minute. And I'll also present a more precise definition of persistent anomaly. But we have lots of examples for why they matter, so I won't get too carried away. But when you have persistent extreme weather conditions, frequently they are associated with one of these persistent anomaly features. And that includes all types of extreme weather, from droughts, cold air outbreaks, floods, extended periods of fire weather, heat waves. So this Pacific Northwest and Western North America event is just one example. But they happen throughout the calendar year. If we're going to study these, we need some kind of a way of identifying them that works equally well in summer and winter. So we'll talk more about that in a minute as well. Persistent anomalies don't have to be anticyclonic. A lot of times people think of blocks as anticyclones that are moving slowly, but you can also get persistent cyclonic weather systems. And one that grabbed recent headlines was the system responsible for the extreme floods in Europe last summer in July that resulted in hundreds of fatalities and 2.5 billion euros in losses. So persistent anomalies can be of either sign, either a positive or negative height anomaly. The questions that really motivated our work are, how do the distribution, frequency, duration, intensity, and ultimately impacts of persistent anomalies respond to climate change? Because when these events happen, again, you have attribution studies, you have the media immediately latching on to the fact that, hey, that something happened that's really remarkable. Was this driven or affected or amplified by climate change? And of course, this is an important question. So a lot of people have been studying this. And one of the things that really inspired us, Walt Robinson and I, to write a proposal about this was we had read in our journal discussion a lot of papers by our former classmate and Brian's former classmate, Jennifer Francis, about how Arctic sea ice loss and Arctic amplification may be increasing the persistence of the mid-latitude flow and increasing the frequency of these types of extreme events. And so there's been so many papers. It took us a long time to write the proposal because we had to read so much of the literature. But this review article by Woolings et al., I think, puts it nicely, that it's a really complicated problem, and there's been low confidence in predicted future changes in blocking, despite a general agreement in the GCMs for a decrease in blocking. But there's a lack of a comprehensive theory of blocking and a pervasive underestimation of blocking occurrence by models. And I know some of the people up there in your department have worked on this as well. But that's, it's kind of a research challenge. So to start with, let's back up and say, well, why would we expect persistent anomalies to respond to climate change? And so what are the mechanisms? Well, there's been a lot of work with blocking and persistent anomalies that have looked at their relation to the mean state flow. And I've just put a few of the studies here. There's also, we know from prior work, there's been some recent work that maybe questions this a little bit, but the transient mobile high and low pressure systems, those transients can reinforce and maintain blocking events. And so if something with climate change affects baroclinic instability or the storm tracks, then that could affect the transients and their interactions with persistent anomalies. There's this question about the lower boundary condition, and it could be, Arctic sea ice reduction, but it could also be sea surface temperature anomalies. And those kind of changes can affect the mean state flow. So it's not independent of these other mechanisms, but that certainly is another approach for looking at why climate change might affect these events. And then lastly, we know in a warming climate, there's increased water vapor content. And there's a class of blocking weather systems that are associated with condensational heating. And so for those types of events, we might expect to see an increase in their frequency or intensity in a changing climate. So there's a lot of different candidate mechanisms, and sometimes there's competing mechanisms, and it takes some work to sort it out. I just wanted to highlight this paper by Steinfeld and Fall 2019, really nice paper on looking at these, what they called moist diabetic blocks. So this is a complicated figure, so we can break it down. So the solid contours show potential vorticity, and small values in the Northern Hemisphere coincide with anticyclonic flow. So this is the block, this sort of red anomaly here. But upstream of the block, there's a moist airstream with air parcels that are experiencing condensational heating. And we know that above a heating maximum, we get reductions in potential vorticity. So when you have latent heat release upstream, that's feeding low PV air into this block and helping to amplify it. But then there's more, because what Steinfeld and Fall showed was that the divergent upper level flow associated with this heating is actually advecting this low PV air westward and holding the position of the block, making it persistent. So not only is the heating, reducing the PV and kind of strengthening the anticyclonic anomaly here, it's also helping to hold it in place and make it persistent. And so this is intriguing. So this was one of kind of the hypotheses we had coming into this work as well. Maybe we'll see an increase in these types of events if we kind of study trends, or if we look at GCM simulations that have warming in them. So going back to this Western North America heat wave, here's this, this upper level anticyclone. And the other thing I should point out that made this event so extreme, there was this little cyclone down here, a little upper level trough that resulted in lower pressure along the coast in Washington and Oregon. And I know Brian recalls this from his days in Seattle, that when you had these really hot days in the interior of Western Washington, the thing that would usually cool it off was the surge of marine air that would come in. But with the lowered pressure offshore, that helped drive this downsloping offshore wind flow. So this little feature too, in addition to the high, really helped to amplify the downslope flow that led to these extreme heat values. But what about the this ridge, the upper level ridge? Now, I'm not sure if you're all familiar with the dynamic tropopause, a constant potential vorticity surface that sort of measures the upper limit of the troposphere. So when you have anticyclonic flow, you can look at the potential temperature on the dynamic tropopause, and that you expect warm or high values of potential temperature on the dynamic tropopause where there's anticyclonic flow. And that coincides with low PV and a higher altitude tropopause. This kind of three-dimensional view shows, here's that ridge, and the isosurface shows the dynamic tropopause. So you can see that that's an area of elevated tropopause with warmer potential temperature there. So where did that come from? In this case, so this shows, again, potential temperature on the dynamic tropopause, and you end up with this big area of really warm anticyclonic value here. But you see that that sort of comes in from the Pacific, and then it cuts off here. So for this case, this really high tropopause potential temperature air comes across the Pacific and it vects northeastward. And if you trace that back, there was a really strong jet out here, and that can be traced back to Asia and in the kind of 15 to 17 June timeframe. So where that came from, I don't know. We haven't looked into that, but certainly there was an advective component of this. But the bottom line is this resulted in a dome of hot, low PV anticyclonic flow over southern British Columbia. And we can look at this a little bit more. So look at this. This is almost a preposterous looking signature here. You have this plume of anticyclonic warm potential temperature on the tropopause air, and it comes up and just cuts off into this beautiful anticyclonic swirl here. But the purple contours here are the column integrated heating. And if you look, there's actually a band of condensational heating extending up out of the tropics up into this event. And so it's sort of like the outflow is then spiraling around. I calculated the potential vorticity, the heating and the potential vorticity tendency. And this condensational heating is helping to reduce the PV in this airstream and contributing to the cyclonic flow. So this looks a lot like the moist diabetic blocks that Steinfeld and Fall were talking about. And so I should have pointed out that cross-section location was down here. So this looks like those types of events that are diabetically enhanced. And this is exactly the kind of event that we would expect might increase in a warming climate. And just to show you the coinciding satellite image, you could call this an atmospheric river, if you like, this plume of moisture and condensational heating coming out of the tropics. So anyway, that's a little bit more. This is work where I'm just starting to look at this case, partly because I find this event it was so fascinating, and also because it affected my hometown of Seattle. I have an extra interest in that. But this goes back to an earlier project, a series of earlier projects that we did before we looked at this event. And this goes back to Rebecca Miller's master's thesis. We wanted a persistent anomaly index that we could use to study changes in persistent anomalies with climate. And then we wanted to apply that to reanalyses, GCMs, idealized simulations, whatever, to see if we could understand what causes changes and trends and persistent anomalies. So one of the other challenges with blocking and persistent anomalies is that there's lots of different indices, and we tried out a number of them. I should say Rebecca Miller tried out a number of them with Walt Robinson and I encouraging her. And the ones that we ended up gravitating towards were going back to Dolan Gordon 1983, the persistent anomaly index. And there were several things we liked about that one. It doesn't, a lot of these indices require a flow reversal, but you can get really impressive blocks that don't have a flow reversal. And also what we found is that even for the cases that did have flow reversal, if you required that, then you missed the first part of the life cycle of those events. So with the persistent anomaly approach, you can really capture the full life cycle of these persistent anomalies. But also you do capture some non-blocking features like jet shifts, which are also interested in. So we favored this type of an index. But the problem with Dolan Gordon is that they had a fixed amplitude threshold and it was sort of set for the winter. And so you couldn't use it to study summertime events. So what Rebecca did is we used a sort of 2 sigma, we looked at the average geopotential height variance throughout the year, and we came up with a seasonally varying amplitude threshold based on the hemispheric average flow variance. And so that way we're sort of defining events relative to a climatological variance background. And we did the other things that Dolan Gordon did as well. And so this is from our monthly weather review paper that came out a couple of years ago, where we presented this index. And we still like it. I think it serves the purpose well, because you just need one variable at one height. All you need is 500 millibar height, and you can apply this easily to any data set, as long as you have enough of a climatology. So we tested this and it matched the Dolan-Gordon results when we kind of ran it for the same, the same conditions. We used it on the 38-year ERA interim reanalysis. And that was the first thing. We looked for trends in that. We also applied it to high resolution impasse simulations that I'll show, and idealized channel model simulations that I'll show if I have time. I probably have too many slides, so I apologize for that. If I get behind in time, I'll just skip a few here and there. I know you've seen people do that before. So we can look with this index and we can see where the persistent anomalies occur in the reanalysis by season, which is nice. And one of the things that we found that we hadn't seen before to be as well documented was this Arctic maximum in the summer. And kind of the cool season centers of action were all as expected, but this summer Arctic maximum is something that emerged when we used the index with the seasonally varying amplitude threshold. And in our paper, we talk a lot about these Arctic features and what causes them. There's kind of import of low PV air from the mid-latitudes. It's quite interesting. They were also there in the cyclonic persistent anomalies. So these cyclonic persistent anomalies kind of show the same centers of action, but there's also an Arctic maximum in the summer. One of the things we noticed for all of the persistent anomalies is they tend to overlap with areas of large flow variance. So the contours on here show the variance of the 500 millibar height, and then the shading is the persistent anomalies. So you see that the persistent anomalies tend to occur in regions of large flow variability. We looked for trends. We expected we might see some, but over the period of record in the ERA interim reanalysis, we didn't see trends in the annual Northern Hemisphere positive or negative persistent anomalies. If we looked seasonally and regionally, we did find some positive trends. There was a positive trend of cyclonic persistent anomalies in the North Atlantic. But overall, the trend was either slightly downward or flat in the ERA interim reanalysis. We thought, well, the Arctic, there's Arctic sea ice loss, Arctic amplification. There's a lot of papers hypothesizing kind of increased waviness of the mid-latitude flow. We thought we would see maybe a signal in the Arctic itself or in the mid-latitudes. But the only signal we saw for the positive, for the anticyclonic persistent anomalies, was a decrease and a pretty much flat curve for the cyclonic persistent anomalies in the Arctic. Now, if we looked at the linear trends spatially, we did see some interesting things. There's a decrease in persistent anomalies over time in the North Pacific and an increase in the Bering Sea and in the North Atlantic. But there's a lot of noise in the calculation, but some of these did pass some significance tests. But that was kind of the summary of the application of this modified index to the reanalysis, is that we liked the way the index behaved, and we were able to identify some interesting features like that Arctic maximum, but we didn't see the trends that we expected to see in the overall frequency, no matter how we sliced and diced it, by season, by region, or both. And so that was our first result. So if you're interested in the details, this paper has them. But then what we did next is Allison Michaelis, who's now a professor at Northern Illinois University, fantastic PhD student, she ran these impasse simulations to study tropical cyclones. And there are 15-kilometer mesh in the Northern Hemisphere, 60-kilometer mesh in the Southern Hemisphere. And we did all sorts of, her paper in geoscientific model development details all we did. We spun the model up for a year. We did careful treatment of sea ice and SST. I'll show that in a minute. But we ran these time slices for 10 different years that sort of spanned the range of INSO. because we were studying tropical cyclones. And then we ran sort of future versions of those same years. And I'll explain how we did that in a minute. But these are high resolution runs. So we thought maybe they'll do well with persistent anomalies. This shows just a sample of one of the simulations of our sea surface temperature. So we're using this OSTIA sea surface temperature at full resolution. And so this just shows that, it's daily varying. You get nice representation of the Gulf Stream, the Kuroshio extension. So it's really, in terms of the gradients, it's a really beautiful lower boundary condition in these impasse simulations. But then we took the GCM average RCP 8.5 delta and applied that to the analyzed SSTs to generate our future SSTs. And so those are also high in resolution. We've just sort of added the GCM average change to those. I mean, you can argue about if there's other better ways to do that, but we wanted a high resolution SST as the lower boundary condition. We know that's critical for the storm tracks and for tropical cyclones. So that was how we did the sea surface temperature. And then for the sea ice, we also treated that really carefully. Let's see, this one's not looping on the left here for some reason. There we go. So we used the GCM ensemble mean sea ice analysis in the impasse model, which took a lot of work on Allison's part to get that working correctly. But the bottom line is that in the future simulations, in late summer and fall and early winter, there's no Arctic sea ice. So we turned the knob all the way. So if there's going to be an atmospheric response to Arctic sea ice loss, we should see it here, because there's no Arctic sea ice left in late July into early October. So that's how we did the sea ice. So it doesn't change between the 10 present day years, and it doesn't change between the 10 future years, but it changes a lot from present to future in the simulations. So here's what the Arctic sea ice looks like on September 15th in the future versus the present day simulation. So it's gone in the summer in the future. So what happened? We hadn't used impasse very much. I won't talk too much about this. In our GMD paper, we felt like we kicked the tires pretty hard on impasse. We hadn't really used it in this way before, and not many people had. It's kind of a newish model. We were really impressed with the way, the only thing we really specified was the sea surface temperature. It's a global model, so it was free to do whatever. And we were really impressed at how well it replicated the reanalysis with the jets and the storm tracks. Some issues, it's not perfect, but it really behaved well as a time slice climate model. But when we compared the persistent anomalies to the reanalysis for the present day simulations, it didn't do as well as we had hoped. So the impasse persistent anomalies are here on the right, and the ERA interim for those same 10 years is on the left. We're underdoing this North Atlantic persistent anomaly maximum, and we're overdoing the maximum in the Pacific, and it shifted. So it wasn't perfect by any stretch of the imagination. And kind of the overall number of anticyclonic events worked out about right. There was a surplus in impasse of the cyclonic events, and a lot of those were actually persistent tropical upper tropospheric troughs. So they weren't really mid-latitude features necessarily. So we weren't too worried about that. It was partly a resolution thing. The impasse had higher resolution than the reanalysis. And we know that GCMs historically, I know there's that Peng Lu and Kevin Reed and others have a paper out looking at this issue with CMIP 5 versus CMIP 6. Historically, models do better in the Pacific than in the Atlantic with blocking or persistent anomalies. And it's really an interesting scientific challenge why the models struggle representing those North Atlantic blocks. I have some suspicions as to what it might be, but we would like to know, because it's definitely, the models are compromised in their ability to represent North Atlantic blocks. But how does the impasse run change present to future? So if we plot the variance throughout the season, remember we have a seasonally varying amplitude threshold, and that's what's shown here. And so we calculated that separately for impasse, being different resolution. And the present day impasse is the solid orange. The future impasse is the dashed orange. So we see a reduction in variance in the winter, in the future impasse runs relative to the present day. And so that means we have a lower amplitude threshold for persistent anomalies in the future, in the winter anyway. But if we look at the annual persistent anomalies in the present and the future, there's very little change. And there's some shifts, there's an eastward shift. There's maybe an increase over Scandinavia and parts of the North Atlantic, but there's also strong decreases in the North Pacific. And so there's some interesting features, like this negative trend in the Gulf of Alaska was also something that showed up in the reanalysis, if you'll recall. So that seems consistent. But overall, these negative trends in the Pacific sort of cancel out the positive trends elsewhere, resulting in a pretty weak negative, a very slight negative overall trend in persistent anomalies. So this was a surprise. We were sort of, based on a lot of previous work and hypotheses, expecting that maybe we would see an increase in these future simulations, especially given that there's no Arctic sea ice in the summer and early fall. So we thought, well, maybe we should calculate the same, maybe it's the persistent anomaly index. Maybe we should calculate the same diagnostics that Francis and collaborators are. So we calculated their meridional circulation index, which is a measure of waviness of the flow. It basically is 0 for pure westerly flow and 1 for pure meridional flow. And we calculated that, and there were some kind of interesting patterns, but for the most part, there was a decrease around the mid-latitudes. And when you kind of look at it, the numbers, this index also exhibited a decrease present day to future. So in these impasse simulations anyway, there was no evidence for an increase in persistent anomalies or waviness of the flow. Rebecca also looked at GCM output and applied the persistent anomaly index there, and it was the same story. So to summarize the impasse simulations, we had these high resolution time slice simulations that we feel relatively good about, except they didn't represent persistent anomalies as well as we would have liked. But they provide a good opportunity to say, well, how does the atmosphere respond to changes in the Arctic sea ice concentration? And at least in these simulations, there was very little change in persistent anomalies. There was a decrease in the cyclonic ones. So these papers, the first one is Allison's paper that describes the details of the impasse simulations. And the second paper shows the kind of climate change results for the persistent anomalies. And that just came out in Journal of Climate last year. So lastly, how am I doing for time? Okay, good. So our former postdoc, Greg Tierney, did these channel model simulations that we were hoping would shed light on all of these sort of real data and geophysically realistic simulations. We did some idealized simulations with a WRF channel model. And this paper also came out in Journal of Climate last year. And so some of the details about the model is it's an aquaplanet. And we ran the model for 1,080 days, and we threw out the first 180 days as spin up. Very large domain, 50-kilometer grid spacing, permanent equinox. So, and there's not even day night. We just set the radiation to the daily value and spread it evenly throughout the day. So these are eternal equinox simulations. And for scale, here's our domain. So here's North America just for scale. And we could run these simulations and use the persistent anomaly index to identify persistent anomalies in the flow. And so kind of following the Dolan-Gordon methodology. So the experiments we did a bivariate set of sensitivity experiments where we have Arctic amplification on the abscissa pointing leftward and global warming on the ordinate pointing upward. So we did 16 simulations. And basically in the Earth system, this is sort of where we are now in terms of the gradients. So Arctic amplification is left and warming is up. So this is kind of, we are here, and with climate change, this is where we're going. And what we did, what Greg did, we fixed the sea surface temperature at the southern boundary. And then we had this profile of varying sea surface temperature, and we did runs with different Arctic amplification. So the ones where it's coldest in the Arctic have the greatest baroclinicity and the strongest jet. But we also did a systematic warming so that we could study the effects of warming separate from Arctic amplification. And we initialized with this jet, but of course, once you run the model, it does its own thing, and the jet, of course, becomes diffuse. You get waves, you develop easterly flow to the south, and the jet shifts northward by 1,000 kilometers or more. So you initialize it kind of where you think it should be, but we let the model run for 3 months so that it could come to its own equilibrium climate. And then we started the analysis. So the initial condition looked very different than what the model's climate wanted to be, which was an interesting lesson. You have to let it spin up for 3 months before you get that right. But what we found is that just looking at the average variance of the 500 millibar height, that increases with warming and decreases with Arctic amplification. So this is sort of what you expect with baroclinic instability and kind of diabetic effects. So the flow variability increases with warming and decreases with Arctic amplification. And the persistent anomaly occurrence does exactly the same thing. Remember how in the real data, the areas of persistent anomaly activity mirrored areas of large flow variability. So maybe we shouldn't be surprised. And the strength of the persistent anomalies did the same thing as well. So this is using a fixed threshold for persistent anomaly amplitude, but this is what we found. So basically, there's competing factors. Warming increases flow variability and increases persistent anomalies, but Arctic amplification, by reducing baroclinicity and reducing the strength of the storm tracks, is compensating that. So it's kind of a wash. This just shows how striking the relation between persistent anomaly activity and flow variability is. It's linear. R squared is 0.94, so it matched really well. Now, again, I should point out this is with the fixed threshold persistent anomaly detection. Earlier, we talked about how it should vary with the flow variance. So even though this result holds really nicely, if we recalculated the persistent anomalies using the 2 sigma threshold, then that increase in persistent anomalies is no longer evident with warming or Arctic amplification. You get a much more complicated pattern. But with a fixed threshold, you see a really nice relation there. But if we kind of use the model climate to define the persistent anomaly threshold, then this is what you get. So the model run sensitive persistent anomaly threshold sort of takes away that nice systematic pattern that goes with flow variability. The last thing we did some local energetics, and I think about some of the great studies that Edmund and collaborators have done. But one thing we were interested in is how do the energetics of these persistent anomalies change with warming? And I'll just show one snippet of this. There's a new paper coming out in Journal of Climate that Greg and Walt and I are working on now. But when you compare for the same Arctic amplification factor, the same jet strength, you compare the cold and the warm run, you see that you get a lot, kind of a stronger anticyclonic jet in the warmer run. And that made me think about the ageostrophic geopotential flux, which is sort of how energy disperses in Rossby waves. So we calculated that. And in the warmer runs, there's a much stronger ageostrophic geopotential flux. So basically, in a warmer climate, the Rossby waves are able to transmit their energy downstream more effectively, which has a lot of implications for exotropical transition of tropical cyclones. And when you get a high amplitude event, it argues for more downstream impacts, more effective downstream impacts. And I think about the work Brian and Edmund have both done with kind of looking at predictability and Rossby wave packets and downstream energy transmission. So this could even also argue that in a future warmer climate, predictability will be affected just by this kind of Rossby wave energy dispersion changing as a function of the base state temperature. But that also should be evident season to season. So to conclude, these channel model simulations, this bivariate experimental design allowed us to separate the baroclinicity influences from the warming influences. And it revealed really clearly that persistent anomaly activity with a fixed threshold varies linearly with flow variance and with jet strength, at least for the range of parameter space that we sampled. And the Arctic amplification reduces the flow variance and the warming increases it. So that in a way kind of explains we have competing influences, and that might be why it's difficult to really kind of isolate the trends in these features in a warming climate. And I mentioned that about the downstream energy flux. So here's the paper that is out on the idealized simulations. As I mentioned, we're working on another one with the energetics, with the available potential energy and eddy kinetic energy budgets. And so hopefully that will be out by in a year or so, provided a favorable review process. But to conclude overall, I've bombarded you with a lot of research here. We started off with kind of looking at one event, but for the overall question in the Earth system, we have competing influences on blocking our persistent anomaly activity. And I think those were clarified by the channel model simulations. We still, it's hard to really reach firm conclusions until the models can do better with replicating the observed persistent anomaly locations. This is especially true in the North Atlantic. And I think if we could rerun our impasse simulations now, I would put more layers in the stratosphere and a higher model top. Just a hint as to what I think might be the problem, but there could be there may be multiple problems, I don't know, but the problem is not solved. And the other thing at the start, I led off with this June 2021 Western North American heat wave, which appeared to fit the model of the Steinfeld and Fall moist diabetic block. Here in our persistent anomaly studies, we haven't done anything to stratify the sample by type to see if there's an increasing proportion of these moist diabetic types. I know some of the work Ping Lu has done has kind of looked at these different patterns. There's certainly a lot of opportunities for more work, I think, to understand how these weather systems are changing in a warming climate. So I'd like to acknowledge Brian, thank you for the invitation, and thank you all for being here and attending. I'll go back to the conclusions, and hopefully that wasn't too much of a fire hose of PowerPoint information, and I'd be happy to answer any questions if we have time for that. I see Edmund has his hand up already.
Edmund, you want to kick us off?
Yeah, sure. Yeah, as you mentioned, there are competing effects with the warming versus the Arctic amplification. But there is actually a third effect, which I don't know whether it's actually present in your channel simulation. Is that under global warming, because of the cooling in the stratosphere, you actually get increased bergelinicity in the upper troposphere, which actually is opposite to what's happening in the on the surface. So it's not clear to me in your discussion, in your description of the model, whether your model actually can replicate that effect also.
Yeah, that's a great question, and when we published Greg's paper, one or two of the reviewers made that same point. It's a great point, and we do get the tropical upper tropospheric warming. We do get shifts in the tropopause. In the impasse simulations, they looked very much like the GCM simulations, and they really did capture that effect. And you're absolutely right. You get increased upper tropospheric baroclinicity. But in terms of the kind of the 500 millibar height variance, it's the lower tropospheric baroclinicity that really seems to be the stronger influence. So you may get stronger upper tropospheric baroclinicity, but that doesn't necessarily mean more energized storm tracks, because you need the interaction between the upper and lower layers. So you're right, there are other effects as well. We could have increased, land sea temperature contrast. And so in the impasse simulations, it's all there. Yeah. In the channel model simulations, we did have enhanced tropical upper warming too. But still the flow variability scaled the way it did, the way we showed. So
but without CO2, you don't have the cooling. So the enhanced stratospheric cooling though.
Yeah, so in the impasse runs we did.
Yeah, in this impasse run,
yeah, but in the channel model runs, I don't, although you get some, in the impasse runs, we changed the trace gas concentrations. We changed the CO2, which you need to do, but we didn't do that in the channel model simulation. So you're right, that effect is better represented in the impasse runs than in the channel model runs.
Yeah, I just want to follow up on, because you mentioned that in your response too, is that when you say it follows the variance, the persistence anomaly, but under climate change, the variance change in a complicated way when you go from near the surface to the upper troposphere. So the variance actually decrease strongly in the lower troposphere and then become positive actually in the high upper stratosphere. So in the lower stratosphere and upper troposphere, because of the competing change in bergelinicity in the lower and upper atmosphere. So you're saying that the 500 millibar is the most important level, because if you look at 300, then the actually total variance may actually increase rather than decrease in the under global warming.
Yeah, that's a good point. And by using 500 millibars, we're sort of following in the tradition of Dole and Gordon. But the thing that's nice about this index is that we could easily try it for 300 or any other vertical level. And I think that's a good suggestion. I think we should do that especially with the impasse simulations. That would be relatively easy to do. And then that might shed additional light on this question you're raising. That's a great suggestion. Because yeah, we've stuck with 500 millibars as being the best layer to use. But you're right that we could get, with climate warming, we could get different changes at different vertical levels.
Yeah, great. Yeah, great talk. Thank you.
All right. Yeah, thanks for your comments. I appreciate that.
Thank you, Edmund. I'm just going down the row here. Jaime?
Yeah, thanks for the very interesting talk. I have a question about your impasse simulation. So the 10-year future and current simulation is based on ENSO phases, right? Is that correct? So can I then interpret your result like the eastward shift of the anomalies, like the PA, a positive PA also, as a result of future ENSO change? Yeah.
Oh yeah, so that's I'm glad you asked that to clarify. So the way we handled the lower boundary condition in the SST we had, La Nina, El Nino, and neutral. And since we used that same sea surface temperature pattern and applied the GCM deltas to that, that means that the future simulations have the same range of INSO phases. So we're basically, we're kind of, we're fixing the sea surface temperatures to have a constrained set of INSO phases. So in a GCM where INSO would be free to change completely independently in the future, you could get different results. The results we have for the future and current in the impasse simulations are for the same INSO, the same set of a range of INSO conditions, which, that's an important point, because it could be that future change will give us a very different distribution of El Nino and La Nina, and that could impart significant changes to the mid-latitude storm tracks. And so we've removed that effect in these simulations.
And related to that questions, why do you choose ENSO phases? Is there any reason for choosing ENSO?
We were using these model runs for multiple purposes, and one of the main purposes was to study the extratropical transition of tropical cyclones, and especially in the North Atlantic. And so given the sensitivity of North Atlantic tropical cyclones to INSO, we wanted to represent the different INSO phases. So the runs were primarily done for the tropical cyclone work, but we realized that we could apply the persistent anomaly question to them as well.
Thank you.
Yep, you're welcome. Thank you.
Thank you, Jaime. Minghua.
Hi, Gary. Thank you for the talk. So maybe I have missed this. Why does warming reduce the PA activity? Do you have an explanation?
Well, so warming increases flow variability. So in the channel model simulations with a fixed persistent anomaly threshold, warming would increase it. But in the reanalysis data and in the impasse simulations, where you have sort of both Arctic amplification and warming, you end up with a small, I would say a small trend. There was a decrease in the cyclonic persistent anomalies, but I would characterize it as a small trend in the anticyclonic persistent anomalies. So I would say that there's competing influences. The warming would act to increase the flow variability. The Arctic amplification would act to decrease it in the lower and middle troposphere anyway.
So I said it oppositely. The increase. So the increase, is there a particular reason why the variability is increased in the warming climate?
Yeah, I think that's a latent heat effect. I think that's, you're seeing, energized baroclinic instability. You're seeing stronger cyclonic development. Kind of the baroclinic growth rate can be increased by added moisture, and I think that's what we see when you just look at the 500 millibar or any other flow, that with the warming you get more energetic disturbances. And
so it's the diabetic heating.
Yeah.
Okay. Thank you.
Yeah, thank you.
Yeah, Ping.
Thank you, Brian. Hi, Gary, nice to see you. Thank you very much for the wonderful talk. Several comments about what you presented. The first one is about the June 30th, that event, extreme event. That's excellent. By our standards, it's also blocking high. It's about 10 days. And at a category 3, that's our experimental scale. It's great. Also, we had an earlier one in earlier June, that month. But that one impacted the Western states more than Canada. It's less extreme, but it's still extreme. We looked at the blocking highs more than the anomalies. There are a couple of reasons for that. The first one is that we also saw cold spells in winter times, such as the one in early February 2021, which is started from north and then all the way across the central United States down to Texas. That one was located to the northeast portion of a blocking high. There's some other more cases we kind of associate with the range also. Another one would be like 2017 February floods in the western states, and even the Hurricane Sandy back to 2012. It's situated to favor the western turn of the track. So we actually follow the term as a triple R that's created by Swain in UCLA back in 2013. The triple R is a ridiculously resilient ridge, specifically referring to the ridges in the western United States impacting us. They are not necessarily blocking highs. Those are by definitions of Gordon and your index you used back in 1983. Sometimes they show up, sometimes they don't, particularly during the winter time when the ridges are really strong near the coast. But actually the anomaly is more westward, close to the trough. Yeah. The next one, I think the models simulate the persistent anomalies less ideal. We saw that also for blocking. The way for the mean state impact on the persistent anomalies, I have been thinking about that for a while. Probably anomalies such as positive anomalies could come from a weakened trough, and in the meantime, probably strengthen the range. So when we look at the positive or negative anomalies, we're probably looking at two overlapping systems. That probably make the things a little more difficult than looking at each of them. So by our recent paper, you mentioned that one with Kevin and several other collaborators that are looking at the GFD of 10 GCM in simulating the blocking highs. Then in that case, because in the detection, we included the climatological eddies more specifically, which is more stationary waves in the detection. So that's included. Then the model's biased climatology, if we replace that part with the observed climatology, then the frequencies, occurrence frequencies, intensity will improve substantially. So that also probably implies we're looking at different systems actually. But anyways, I like your talk. It's so great. Thank you very much.
Yeah, thank you. Those are good comments, and I'll try to keep track of your. I know you'll be doing more with the CMIP 5 to CMIP 6 analysis, and I'll be interested to see what you find, and if we can get better simulations of that North Atlantic blocking, that would be reassuring. Then we would have more confidence in the projections. Yeah, definitely. That's for sure. And also, by the way, our approach will be hopefully probably open to the public by the end of this summer. And there will be an undergraduate hire intern recruited in the GFDL collaborators. We're working together to get the package hopefully ready for use by the end of the summer. Excellent. Great. Thank you. Great. Thanks.
Thank you, Ping. We're running a little late. I just had a quick question for you, Gary. I mean, that event you presented, which I remember, was amazing. And so I was curious with your PA index or anomalies. I can't remember exactly what you showed. It seemed like more of an average or changing climatology. But I was curious about the tail of the distribution. And I mean, did you see any really changes in standout, anomalies in your data set from present to future?
Yeah, well, we do have that. I don't think we put that in the paper. There weren't, we looked at, we did every diagnostic, duration, intensity, aerial coverage, all of these statistics. And I don't recall, I know that for the reanalysis data, we didn't see any trends in the tail. I believe we did that calculation for the impasse simulations, but I don't recall. I think if we had, I don't recall seeing any dramatic change or shift, because if we had, we would have reported on it. I don't remember exactly what the PDF looked like, but yeah, we didn't see future blockbusters happening any more than present day ones, is my recollection. But that's a good question.
Yeah, I only brought it up because you mentioned that group that with that event they attributed to climate change right away, within days. So So I was trying to make a linkage there a little bit more, but
yeah, and I feel like the impasse model should be able to represent events like that. The only question is, there was that really strong jet that came across the Pacific that was traced back to Asia. You know, it's probably worth tracking that down to see, you know, what was going on. But I feel like especially with a 15-kilometer mesh, impasse should be able to represent an event like that. I mean, the GFS forecasted it. At day 5, GFS had that ridge. But let's see, it looked like Edmund may have another question.
Oh, I don't know whether I should ask, but I just want to get a quick comment from you, because you mentioned that with warming, the variance increase, but that's actually a controversial thing. There's been a lot of discussion about whether increasing diabetic heating actually would give rise to increased additivity. I think in some idealized model, they found that it increased and then flattened and then decreased, and we are close to the peak of that, because the structure of these storms change when you have too much moisture in the atmosphere, and it becomes less efficient very clinically. And I think Isaac Held always has 20 years ago, I actually argued that with increased moisture, you actually, the eddies transport more latent heat, and so you don't actually need as strong a circulation for the same transport. So do you really see a clear increase in variance in your simulations?
So I noticed in the second bullet here, the caveat is at least over the range of parameter space sampled here. If you're talking about like Lapierre and Held, they turned the knob way farther than I mean, in their warm regime, they ended up with kind of more of a tropical cyclone type regime. And I think you're right. You know, we're not sampling the wider parameter space here. And even with the warmer runs we did, we started seeing tropical cyclones forming in the southern part of the domain. And even at 50-kilometer grid length, we were getting tropical cyclone-like systems. And so I think if we made it much warmer, then we would start seeing a transit. We get more I mean, this is a full physics model. So then we would be getting extratropical transition events and all kinds of other things going on. But even in the runs we did, we were starting to get tropical cyclones. And so we didn't keep making it warmer and warmer, but it could very well be, I understand what you're saying. And I think that probably it would change into a different regime if we kept warming it. But the range of warming we're showing is sort of consistent with where we are in the Earth system and where we are projected to go in the Earth system, say in the next 100 years. I think Lapierre and Held went beyond that.
Yeah, I was referring to some more recent study by sort of, I think, Farr et al., O'Gorman, and
okay.
People. Yeah, they look at Berkeley instability in just raising idealized moist model, raising the temperature.
Yeah, I should look at those papers, but what we found is that, you know, the warmest run we have, you know, showed the most variance. But it'd be interesting to, if Greg has moved on, but we've inherited his version of the model, so maybe we could do some additional warming runs and see if it does start to drop off. I think that's a very good point again.
Mm-hmm. Yeah, great. Great talk.
Can I ask
Yes.
one last question? Yeah. So you mentioned a little bit about predictability, and I'm curious, what is the predictability of these persistent anomaly events, and how well the operational models predict these events?
Yeah, one of the things we wanted to do was to take this this algorithm and apply it to the GFS or the GEFs, and just sort of see, you know, what does the skill look like as you go out. We haven't done that yet. I think that would be a really interesting thing to do. We've looked at some individual events, and like I looked at the predictability of that June 2021 heat wave event, and the GFS was onto that. I mean, I remember even on this email listserv that some of us are on, that people were talking about that before it happened. And people, the first comments about that are, oh, there's something wrong with the models. They're forecasting 115 degrees for Portland or something. And what's wrong with the GFS, you know? But man, it was on it. And so there was a lot of predictability for that event, and kind of suggest that the larger scale features coming across the Pacific were at work. But for the events that are more strongly diabetic, these moist diabetic blocks, probably there's going to be lower predictability there, because you're relying on the model representation of convection and microphysics, where there may be getting the heating profile right is critical, and there's challenges there when you get out to very long lead times. But yeah, I think there's a lot more work that could be done, and I would like to certainly, I don't know, it wouldn't be that hard to put that algorithm into the GEFs and just see what the skill is like. Maybe you're aware of people that have done that work. I haven't taken that step. It's a good suggestion, though.
Thank you.
Great. Well, thank you very much, Gary. Thank you, and give him a big round of applause. So, so we're going to end the seminar, although the students, I see several students on here, and Gary's available to 1:30. If you're a student, please stay online. I'm going to stay on for a few more minutes and maybe hand it over as a co-host to someone. But thank you everyone for joining us here today.
Yeah, thank you. And thanks for all the good questions. That was great. Some great suggestions there.